Okay, so thank you organizers for giving me the chance to speak here. I am going to talk on a new class of examples of quasi-geodesic anosov flows. This is a joint work with my supervisor, Sergio Fenley. So what is a quasi-geodesic flow? A flow phi-t on a Riemannian manifold is called quasi-geodesic if the flow lines of the lifted flow in the universal cover are length minimizing up to some multiplicative and additive constants. So why these quasi-geodesic flows are interesting? So they are very useful tool in the study of anosov flows and their underlying manifold. So especially in the large scale geometry, this is a very important tool. Like if we have a hyperbolic manifold equipped with a quasi-geodesic flow, then we can define a continuous map from the manifold to its sphere at infinity, that is the Gromov boundary. And these maps are extremely useful, and it's a big area of study, and a lot of people like Cannon, Thurston, Gies, Caligari, Penley, Franknell, and others, they have contributed in this area. So let's see what are the examples of quasi-geodesic flows. So suspension flows are quasi-geodesics, like we're talking in dimension 3. So suppose we start with a map on a surface, maybe punctured or closed. So the mapping torus of the map is equipped with a natural suspension flow, and these flows are quasi-geodesic. But this is probably the only known class of examples in dimension 3 of quasi-geodesic flows. So in this talk, we are going to construct a new class of quasi-geodesic flows, which are not suspension. So let's review the construction. So we start with a derived from anosov map on two torus. So this type of maps have a fixed source point and a hyperbolic one-dimensional attractor. So DA maps are introduced by Smale in 1960s, and they are really useful in the study of dynamical system. So next, we are taking the mapping torus of the DA map and consider the suspension flow inside the mapping torus. So obviously this suspension flow is quasi-geodesic. So on the left hand, we are showing what is going on in the universal cover R3. So the suspension flow has a repelling periodic orbit gamma, which is coming from the fixed source point on the torus. So next, we are considering a solid torus neighborhood around the periodic orbit gamma, and we are taking out from the mapping torus. So the resulting manifold is a manifold with boundary. The boundary is homeomorphic to torus, and we can restrict the suspension flow on this new manifold with boundary. In that case, the flows enters inside the manifold, intersecting the boundary torus, right? Okay, so now we are taking another copy of the same manifold, but equip it with a reverse flow. So now the flow lines are going outside of the manifold, intersecting the boundary. So we have two manifolds with boundary, both of them equipped with a flow. In one manifold, the flows are going out along the boundary, and in one manifold, the flows are going inside along the boundary. Now glue these two copies of the manifolds along their boundaries, but not with the identity map. We use a rotation to identify the boundaries. So these two semiflows match perfectly along the boundary, and we get a flow on the whole new manifold. Okay, so this is the flow we are looking for. So this is actually a very famous construction by Franks and Williams, and this was the first example of a non-transitive anosov flow. Now we are able to show that this example is also a uniformly quasi-geodesic anosov flow. So the construction can be generalized into a bigger class of example using the techniques introduced by Bonatti, Bejoin, and Yu. And it is easy to see that the underlying manifold is non-hyperbolic because the boundary torus is incompressible inside the new manifold, and it actually gives us the JS decomposition such that both of the pieces are adoroidal. Okay, so this is a new class of examples of another flows which are not suspension flows. So that's it. Thank you so much.